All right, here's a little help on worksheet 1B, all right, in case you need it for any reason. Okay, so here's our data from 1A. Okay, you can see the position versus time data on the left. These little arrows up here just mean it's a vector, which means it has like a directions, positive or negative, so don't worry too much about it, okay? All right, okay, so what you want to do is you want to look in this time interval is 1 second. This position change, the delta, is 12, okay? This time interval is also 1 second, and its delta is 20, okay? So you're going always for a 1 second interval, right? Because we only want to look in each interval, okay? So 38 to 66, oh, calculator. It's too early to do this in my head. Let's see. Okay, 66 minus 38, okay, 28. Okay, 102 minus 66. 36. Okay, so see what I'm doing here? So this one is 44. Okay, and then 198 minus 146. Oops, 198 minus 146 is 52. Okay, all right. So what you're doing is you're trying to just look like, right? Because we know the velocity is not constant, right? So in each time interval, we're trying to see on average, right, average velocity, on average, how fast is the cart moving in that interval, okay? All right, so in the first second interval, it's moving 12 centimeters in 1 second, so its velocity is 12 on average, okay? We'll do the time in a minute. And the second interval, it's going 20 centimeters in 1 second, so the average velocity is 20 centimeters per second. 28 centimeters in 1 second, 28 centimeters per second, etc. Okay, right? So these are telling you the average velocity in that 1 second interval. Okay, again, it's not how fast it's actually going at one moment because it's in a whole interval. Okay, so that this number here comes from calculating from here. This is stuff we're going to ask on the quick quiz. Okay, so make sure you understand how this table is made, all right? So what I did was I subtracted this time interval for here, this position change here. In that 1 second interval, if I go 12 centimeters in 1 second, that gives me an average velocity of 12 centimeters per second in that interval. Okay, does that make sense? So it's moving 20 centimeters per second on average from 1 to 2 seconds. It's moving 44 centimeters per second on average between 4 and 5 seconds, etc. Okay? All right, now, if we want to create a velocity versus time graph, velocity centimeters per second, time in seconds, okay? If I wanted to do a velocity versus time graph, this is an instantaneous velocity. We don't write it, but it is, right? Because it's just at one time, because I'm going to plot like a point. Right? So it needs to be at one single time, how fast is it going, okay? So this number that we calculated doesn't really tell us how fast it's going at a time because it's really in the time interval 0 to 1 seconds, okay? What we learned in worksheet 1A was if we get the average velocity in an interval, say 0 to 1 seconds, we know that that average is also equal to the instantaneous velocity at the middle time, okay? So the middle time between 0 and 1 is 0.5. So if I wanted to create a graph where I needed an instantaneous velocity, I can use this average, but it's also the instantaneous at the middle time, which is 0.5 seconds, okay? Same thing here. From 1 to 2 seconds, on average, it's going 20 centimeters per second. That's also the instantaneous at the middle time of that interval, which is 1.5, okay? Right? So that's why these are going to be graphed at the half time, at the half times, okay? All right, hopefully that makes sense a little bit. Okay, then you're going to go ahead and plot this graph. I'm not going to plot it out because this is so tiny on the iPad, okay? But basically 0, 1, 2, 3, 4, 5, 6, whatever, 10, 20, 30. Okay, but you have to count this out better, okay, right? I'm just not really doing it. I don't know. Okay? All right, anyway, so you're going to go ahead and graph this, and it's going to turn out whatever it turns out like, okay? But you need to actually graph it for real. Count the squares, whatever, okay? And you're graphing this set of data is what you're graphing here, okay? So you have to do it at 0.5, 1.5, that's where your points are going to be at the halves. Okay, your points are going to be at the halves. All right, does that make sense? Okay, so you're going to get all that done, but make sure you understand how this table was created, because this is what we're going to ask on the quick quiz. Okay, using the graph you created, draw a line of best fit. Okay, I did that. Using that line, find the velocity at each clock reading, okay? So now instead of the half times, I want the actual whole times. So you're going to need to look at your graph, right, and see what the actual velocities are at the seconds, not at the half seconds, okay? Including 0, which should be your y-intercept, all right? Hopefully if you look at that and you can do all that, you're going to see that this is 8, okay, is where it should cross at 8 centimeters per second, 16, 24, 32, 40, 48, 54, no, 56. Oh, I don't even have to write centimeters per second because it's right there, okay? So from this table or the one above, the velocity increases by 8 centimeters per second every second, okay? So you can see this table jumps by 8. This table here also jumps by 8s, right? Because this is still a 1 second interval, even though it's going half to half, but it's still a 1 second interval, okay? All right, so this velocity is increasing 8 centimeters per second every second. Okay, that's what makes this graph now a line. This is different than the velocity graph we saw before, right? Because before the velocity was constant and the graphs were flat. Now they're diagonals, okay? All right, if I wanted to keep going, I could just keep adding 8, okay? So 56 plus 8 is 64, right? And then another 8 is 72. Another 8 is 80. Another 8 is 88. Okay? All right, so that pattern is just going to continue as long as you want, as long as you keep allowing the car to speed up. So I'm going to add 8 centimeters per second every 1 second that passes, because that's the rate that the velocity is increasing. Okay? All right. So if I go here, now I can kind of combine some of this information. So at 5 seconds, my velocity was 48. And then if I look up here at 5.5, it was 52. Okay, and then at 6, it was 56. And then at 6.5, I think it was 60. Oh, we didn't have a 6.5. We're going to have to figure that out ourselves. 60. Okay, so now this ratio, right, is going to be 52 to 48 in 5.5 seconds minus 5 seconds. So this is going to be 4 centimeters per second now in half a second. All right, which still is a ratio of 8 centimeters per second in 1 second, right? That ratio is still the same, because just like when we did next x, right? If I wait a shorter time, it didn't get as fast, right? If I wait a whole second, it gets 8 centimeters per second faster. But if I only wait half a second, it only gets 4 centimeters per second faster. That makes sense, okay? And similarly, I can do it for 2 seconds. So if I do 4, so I do 40, 6, 56, 8 was 72, and 10 was 88, okay? So now if I look at this ratio, let's do 56 minus 40 over 6 minus 4. Okay, so that's going to be 16 centimeters per second. But now I'm waiting 2 seconds, right? Because if I wait 2 seconds, it's going to get faster than if I wait 1 second. But still, look at this. The ratio is still 8 centimeters per second per second. Every 1 second, the car is still getting 8 centimeters per second faster. Okay? All right. So what pattern I notice is that ratio is always the same. Okay? And that ratio tells me how much the velocity increases every second. Okay, right? Okay, the name of this ratio, which we'll get to if you do this in class, unless if you have a sub, then your teacher can catch it when you get back. The name of this ratio is what we call acceleration. Okay, and acceleration, we think it means the velocity increases, and in this case it does, but really it means changes. Okay, because we're going to get to this a little bit more in 3B, but let's try not to start saying increase. Let's say changes. Okay, so the acceleration is basically the change in velocity divided by the change in time. or delta V over delta T, okay? Change in velocity over change in time. That's what it means to accelerate, you changing your velocity over time, okay? It does not necessarily mean getting faster, okay? So let's try to not start saying that, okay? The units for that, the change in velocity is centimeters per second, and then the change in time is seconds, okay? So this is kind of a weird unit, and this is sort of a hard concept because it's a rate of change of a rate of change, okay? But if I say this in a sentence, I would say something like, for every 1 second, the velocity, in this case, increases, because it's a positive, by 8 centimeters per second, okay? So in general, I would say the velocity changes per time, but if I have a number, I need to say whether it's increasing or decreasing, okay? So for every 1 second that passes, the velocity increases by 8 centimeters per second, and that is what's called acceleration, okay? All right, I'm gonna make another video for the pirate, I think, so I can do the pirate, but that's the end of that.